Okay, this will be lesson 2 of chapter 6. This should be a shorter lesson. So what we'll talk about here is what's called the emission of light. And there was a mystery in the 20th century involving something called emission spectra. So essentially what they did is once they found out that atoms release light, and they were able to control exactly which atoms are releasing the light, and they started looking at the colors that the different elements were releasing, both elements and compounds. Every substance will actually give off a signature of light coming off of it. So if you heat up an atom, in this case, if you heat up a bunch of, say, neon, they will actually release their light. And it'll release a very characteristic color of light. And from that you can deduce the electronic structure of those helium atoms, or I'm sorry, the neon atoms. So what we see is something called a line spectrum with discrete wavelengths. What this means is that if you take this light and you break it apart, what you'll see individual wavelengths present. Even though to our eye it looks like red, if we break that down, we can see actually distinct lines in the, as you'll see in a minute here, distinct lines in the red portion of the spectrum. And in order to do this, we'd have to pass, if you pass white light through a little slit and then through a prism, the prism is able to break light up into its individual colors, what we call the colors of the rainbow. And if you shine light from an atom, if just one substance is releasing the light, what you'll get is you won't get the full spectrum, but you'll get distinct lines in that spectrum. And each line corresponds to a certain wavelength. And that wavelength then corresponds, as we saw earlier, to a certain energy. So what this will be showing us eventually is that the atom is releasing, its electrons are releasing a certain amount of light, a specific amount of light. And this specific amount of light relates to the electrons jumping between different energy levels as we go along here. And that's essentially what we'll be able to see in the second lecture. So here is a diagram that explains this emission of light. And a guy by the name of Niels Bohr actually first came up with this idea, and the Bohr model of the atom is actually based on him. So if you recall, we did Bohr model, and we'll actually take a look at it later, where you can think of electrons are circling around the nucleus as planets around the sun. That's actually due to Niels Bohr, who first proposed this idea. So electrons, according to Niels Bohr, can only occupy certain orbits, and these orbits, each one of these orbits essentially corresponds to a certain energy. So an electron on this orbit then has a distinct amount of energy. And what you see here in this diagram essentially is energy level 1, 2, 3, 4, 5 and 6 and on to infinity. And electrons technically can jump between these energy levels. So here you'll see this arrow, green arrow, corresponds to an electron jumping from energy level 3 to 2, or from 2 up to 3, and that will actually correspond to a certain amount of energy. And this will be given off by the element as a certain frequency of light, because if you know the frequency, or we'll say if you know the energy, remember, then we can find out through the equation we saw last time. We can find the frequency, and if you know the frequency through the second equation, we can actually find out wavelength. Is the idea. So this is what this model explains, and this whole diagram actually is a diagram showing the different possibilities. If you have, this is actually for a hydrogen atom, the many different possibilities of a hydrogen atom releasing the different colors of light. And the green portion here is what actually we saw in the previous slide of these 4 bands. If you go back, these are the 4 bands, 1, 2, 3, 4. These 4 bands are released in the visible portion of the spectrum. This is of actually hydrogen. This emission spectrum is of hydrogen. Famous emission spectrum of hydrogen. And what you see essentially is only these 4. Now there are other light given off by hydrogen, but you don't see it. This short one is actually in the infrared because it's a small energy change that corresponds to a lower frequency light, which is in the infrared, and this is actually in the UV, in the ultraviolet, a very high jump corresponding to a higher energy, and we'll see that as we go along. So electrons, so here are a few rules. This is a bit strange. We got ourselves a 2 here. This should have been a 2. That should suffice. And electrons in permitted orbits have what's called allowed energies. And these energies are what decide how much light and how much energy will be radiated from the atom. And what happens is energy can be absorbed or emitted, released, whenever electrons move between these allowed energy states. And again, that's given through this equation. So when an electron, say, jumps, so here's your nucleus, and here's the first energy level, here's the second energy level. When an electron jumps from here to here, a certain amount of light is given off. And that light given off is essentially the difference between these two energy levels dictates how much energy the light has, which therefore tells you what the frequency of light is, which then gives you the wavelength of light. So another way to think of this is think of a ladder, and this essentially shows this is a strange property of matter at the microscopic level. So the electrons, think of the electrons as existing on the different rungs of this ladder, and the further the electrons are from the nucleus, we'll pretend that the nucleus is right down here, and the further the electrons are from the nucleus, the more energy they have. And there is no such thing as in-between energy levels. So the electron can never exist in between these two rungs. It's kind of strange. But electrons can only occupy these amounts of energy. So at the ground state, an electron that's in the ground state is in its lowest energy state. So for example, this first rung will be occupied by a number of electrons, and the second will be occupied by a number of electrons. So in a multi-electron atom, all these essentially will be occupied. But each one will be in its ground state, essentially its beginning state. And then those electrons can become excited. They can actually be promoted to upper energy levels. And there are plenty more rungs going up, many more as we go up. And that will be called an excited state. So what we can do now is we can calculate how much energy, the change in energy, how much energy is released whenever electrons jump between these energy levels. And this is a strange equation. We're really not going to do too much with this equation, but this is just to show you that you can be very mathematical and you can calculate exactly how much energy is released when electrons jump between energy levels. This NF is its final destination, and then NI is its initial destination. And then N here you'll see means the energy level. So N can be 1, 2, 3, essentially the energy level that it's jumping from. So delta E, we said the change in is final minus initial, and through this equation you can actually get the change in energy. Now this R actually refers to something called the Rydberg constant. So through here you can actually determine, through this equation, which we won't really use, you can determine how much energy is released between in the jumping of electrons between two energy levels. And this equation here, it says, can really only apply to the hydrogen atom. Anything above hydrogen, there are interactions between electrons that make it difficult to really put them in an equation. It gets pretty complex. And what you see is here we see 4 emission spectra. This one is actually that we've seen of hydrogen. This is actually backwards from what we've seen earlier. But hydrogen shows 1, 2, 3, 4 lines in the visible spectrum. Helium, the second one, is actually for helium. Helium shows a few more. Here mercury actually shows even more. And then uranium, you'll see, shows a lot of lines in its spectrum. In fact, uranium, if you recall, is toward the bottom of the periodic table, meaning it has the most electrons. Therefore, its emission spectrum should show quite a bit of lines. This means that many electrons are jumping between the energy levels. And recall that there are more lines out here in the infrared. There are many more lines out here in the ultraviolet that we can't really see. But the biggest thing to understand is that we can actually take a look at the lines, and by these lines we can actually determine the element that is present, the substance that is present in whatever is releasing that light. And this is actually how we are able to identify what kind of elements or substances are present in different stars. So what we do is we take the light from those stars and we analyze that light, and from that light we can determine what's present. Very important technique in astronomy. What we're going to finish up with is a discussion about the wave nature of matter. What we saw last time, recall, is that light can be thought of as a light or as a wave or a particle. So light has particle or materialistic properties. Light has material properties, we said. So the opposite should be true. Mr. de Broglie said, well, the opposite may be true, and in fact, it is true. The matter actually has a characteristic wavelength. And here is the equation that gives us the relationship between the mass of something, which any object that has mass is considered matter, recall. So all forms of matter can have a characteristic wavelength. This is very strange. So any particle that you have, whether it's a proton, an electron, an atom, anything bigger, even something like a baseball, technically as it travels, actually travels in a wave-like fashion. And this is actually true, and this is especially seen at the microscopic level. This is very measurable. Something big like a baseball or a basketball, you won't be able to see this wavelength. The wavelength will be way too short to notice. But anything at the microscopic level, you can definitely see a wave-like pattern. So protons, for example, definitely travel in a wave. So this is strange, but this, because we're talking about electrons, recall, we want to discuss the electrons, how they're arranged around atoms. A very important insight here is that electrons move around the proton in a wave. So electrons actually, as they're moving, are moving in a wave-like fashion, just like light has a wavelength. And there's actually a very important piece of machinery in the scientific world used to do an enormous number of experiments. One of them would be, for example, to take pictures of this is viruses. Viruses are so tiny that it's impossible to see them with a regular microscope. So what they have is they created something called an electron microscope, and that's because electrons can have a much shorter wavelength, and we can utilize that wavelength. Essentially, we can use electrons just like we use light to see things. We can use electrons to see things. Is the idea. So this is a very important technology that's essentially coming from a matter having wave-like properties. And we're probably going to finish up with this example. The example says, what is the wavelength of a hydrogen atom moving at a velocity of 5.97 times 10 to the 5th meters per second? So what we're going to do is we're actually going to use the equation, the de Broglie equation, which shows that matter has a characteristic wavelength. Wavelength is essentially associated with waves, so matter has wave-like properties, and the equation is h over mv. Now, I didn't mention too much about this equation earlier, but h is your Planck's constant, which, if you recall, was 6.626 times 10 to the negative 34th joule seconds. And if you recall, the mass, technically in this case this is mass, and in this case this is actually velocity. This is not frequency. This is velocity. This is from physics, and this is meters per second. So the idea here is we want to plug in the mass of a hydrogen atom. Now, the mass of a hydrogen atom, because you have yourself joules. Joules, if you recall from the last chapter, comes from energy, and a joule is actually, the definition of a joule is kilograms times meters squared per second squared. If you subdivide the unit of energy, joule, you'll actually get this essentially as the unit. And the reason I do this is because the mass in our case, because our units have to match in any equations that we work with, our units have to match. So our mass will actually have to be in kilograms. That's essentially the first order of business, is to put mass in kilograms. Now the way, if you ask what is the mass of a hydrogen atom, is what? The mass of hydrogen is what? Well, you could probably look up the mass of hydrogen, of a single hydrogen atom in some sort of book, but actually it's given to us on the periodic table. If you take a look, the mass of hydrogen is actually 1.01 grams per mole from the periodic table. This is the molar mass of hydrogen. Well, since we know how much a mole is, we can actually determine the mass of a single atom. And so let's do this little conversion. So we got 1.01 grams. This one is a bit, oh there, a little better. In 1 mole. Let's go ahead and convert from moles to atoms. We know that a mole, so we have mole at the bottom, we'll put mole on top. And then we're going to convert to atoms. We know that a mole, if you recall, has 6.02 times 10 to the 23rd atoms. In fact, we're going to be celebrating Mole Day here in about a month or so. We actually celebrated on the 23rd of October, if you recall, 10 to the 23rd. So let's go ahead and do this little conversion, and what we'll get is we'll get the mass of a hydrogen atom per atom, the grams per atom. So we'll do 1.01 divided by 6.02 times 10 to the 23rd. So this gives us a mass of 1.67778 to be exact, times 10 to the negative 24th, in this case grams. To convert this to kilograms, essentially what we'll have to do is a kilogram has 1,000 grams, and so we end up dividing by 1,000 or moving the decimal place to the left 3 times, which gives us 10 to the negative 27, 1.678 times 10 to the negative 27 kilograms. So this, we had to put the mass of a hydrogen atom in kilograms, and it's admittedly a very tiny number. And now we can actually plug it into our equation and solve for the wavelength of a hydrogen atom. So the wavelength is equal to h, which is a constant, 6.626 times 10 to the negative 34th joule seconds. Divide that by kilograms, which we got 1.678 times 10 to the negative 27 kilograms, multiplied by our velocity, and in this problem looks like our velocity is 5.97 times 10 to the 5th meters per second. So 5.97 times 10 to the 5th meters per second. And if we do this right, what we'll see is that everything cancels out except meters. In fact, we have inside of the joules idea, we have maybe I can take a look at this. If I break this down, if I break that down into meters squared, seconds squared, we'll see that the seconds cancel out completely. One of the meters cancels out, kilograms cancels out, and what's left essentially is a meter. So if we calculate this, we'll get ourselves a meter. So let's try this. Let's go ahead and put this in our calculator and see what we come out with. And why don't we multiply that by, you can do this right along with me, and we should get ourselves an answer, a final answer that says something like 6.615 times 10 to the negative 13. So using significant figures, it looks like we had 3, so why don't we do 6.62 times 10 to the negative 13 meters. And this essentially is the wavelength of a hydrogen atom flying at a velocity of the given velocity at 5.97 times 10 to the 5th meters per second. So every form of matter has a characteristic wavelength. That of hydrogen is 6.62 e negative 13. And that concludes lesson 2 of chapter 6.